Good morning, everyone. I hope that you guys are having a good start to your day. It is the 1st of July, so happy new month. Um, we are going to be continuing on the stuff that we started yesterday. One thing that I did not do yesterday that I I told you that I would, and I apologize for this, is send you that link to show you how to log in through an authenticated Texas State account. So if you are fantastic. If you are not logged into Texas State and maybe you joined Zoom as a guest or something like that, um, pay attention to the link that I will send later today as an announcement. Now, um, other than that, there's not really any announcements. There's nothing due today. You have a quiz tomorrow. I'll be posting about that quiz a little bit later, give you some ideas about that. I am almost done writing the practice exam for exam number one, and I will get that posted as soon as it is ready to be posted. Um, and hopefully that will be before the end of the day. Then I'm going to move on to practice exams for two, three, and the final. Um, We are in lecture number one, and we will move through that, and then we'll move on to lecture number two, or day number two, I guess it would be. I mentioned this yesterday. Um, sorry, I mentioned yesterday that I like to kind of move through things kind of organically. Um, I'm not planning on being very like hardcore and abrupt about, oh, well, this is only to be covered on day one. This is only to be covered on day two. If we make a lot of progress on something and everyone's positively responsive, then we'll proceed. Um, with the rationale there being, maybe that would leave either time for additional review before an exam or just, hey, we don't have, you know, I'll be holding office hours instead of a lecture period. So that's what I'd like to do. Now, with that in mind, I've got to get a couple things going before. Let's see, we'll go with that. Yeah, blow this up. So yesterday, what we were talking about, and there's probably something blocking the center of the screen, which does not help you guys see any of that slide at all. But I've just got to kind of do a little bit of rearranging on my screen, and I'll have that squared away in just a second. Go. Um, we left off yesterday, and we were talking about. Oh, goodness gracious! Sorry. Also, whenever we move positively through things, then it leaves the opportunity for me to have like a technical screw up and not know what's going on with my computer. And then I don't feel terribly guilty about it. Instead, I just feel embarrassed about it. Okay. Yesterday we talked about properties and we talked about chemical properties and physical properties. And we kind of highlighted some important like keywords to look out for. For example, when you talk about a physical property, you want to talk about the state of something changing. So something melting, going from a solid to a liquid, is a good example of a physical property. Now, another thing that's a physical property is the density or its visual appearance. Now, with respect to a chemical property, some of the keywords that you want to look out for are rusts or ripens or burns or something decomposes. Typically, when it comes to a chemical property, I always kind of think about chemical properties versus physical properties as like my base understanding is going to be okay, if something looks different, I'm going to lean towards it being a physical, or if something looks a certain way, that would be a physical property that I'm going to kind of assume. Whereas if something like tastes different or smells different, that would be a chemical property. And whenever I say different, I mean like from its kind of original state. So if I poured a glass of milk and then, came back 20 minutes later and I was like, huh, it looks a little bit different. Oh, well, it looks different because there's condensation on the exterior of the glass. Okay, so that just means that the temperature of it has changed. That's a physical property. But then when I smell it now versus when I smelled it an hour ago or 20 minutes ago, oh, it smells considerably different. What's happened? Well, chances are some sort of chemical reaction has taken place. And chances are, if it takes 20 minutes for a chemical reaction to take place, then something's happened. Someone's poisoned it or something like that. I don't know exactly, but milk doesn't take 20 minutes to sour and go bad. It takes days and, you know, exposure to the atmosphere. So these are all kind of good ideas of what to look for when it comes to chemical or physical property. These are good keywords. Now, some examples of a physical change. So when you talk about a physical change or a physical property or a chemical property, it's always important to think about, well, changes that these substances undergo. A good example of a physical change is where no bonds are made or broken. Now, what does that look like at kind of your visual, the naked eye level, also what we would call kind of the macroscopic level? Well, if an ice cube melts, that's a physical change. The state of that water has changed. The shape of that water has changed, but it's still water. Whether it's frozen, the chemical makeup of water is the same as the chemical makeup of ice. Now, when you separate components of a mixture, could anyone, let's see, is there anyone from the Houston area? Give me a number in the chat if you're from the greater Houston, Texas area. Okay. Now, for those of you who are from Houston or not from Houston, but know this, what's one of the biggest industries in the greater Houston area? Fair enough. True. Okay. Let's go for another one. I'm thinking of a three-letter word that starts with a G. Yeah, there we go. Oil and gas. The oil and gas industry is huge around Houston. And if you drive down to Galveston through Houston, chances are you're going to see lots of refineries. Now, those refineries, those have any of those oil and gas refineries, what they're doing a lot of is separations. And they have the super high towers. And does anyone know what those towers do or what you're doing, what is being done in those towers? And I know that this is one of those things that I said exactly what I would not do, where I would ask an open-ended question and look for a response in the chat. What is being done in those towers is different compounds are being separated from one another. So, for example, in an oil and gas refinery, one of the things that's separated, or several of the things that are separated from one another, would be kerosene is separated from propane, which is separated from octane. These are all hydrocarbons. These are all combustible substances. You can burn them and get energy from them. Now, does anyone know what, or sorry, those are all being separated in these towers, and they're being separated based on their differences of their physical properties, their boiling points. So basically, this liquid, this mixture of lots of different gases is heated up, and they are going to all vaporize. And then at different points in these towers and these stacks, they're going to condense and they're going to liquefy and then they're going to be extracted. So that is a separation based on physical properties. So you're taking something that's a liquid and you're converting it to a gas. Whenever it's converted to a gas, well, then you can capture it. And in this case, whenever I say gas, I mean like gas like O2, something that's in the air, as opposed to like gasoline. Okay, so that separation is an example of separation based on physical properties. And that is a physical change, or those are physical changes that you're looking at there. Another physical change is when you make a solution. And whenever I say that, I'm talking about like if you got table salt and you added it to water, you would make a saltwater solution. There's no chemical change that's taking place there. That seems a little bit confusing because, if you think about NaCl, table salt, well, that's not, sorry, that will dissolve into water as Na plus and Cl minus. Now, this right here that I've just highlighted, NaCl, is Na plus and Cl minus, but it's as a solid. So a good word to look for a physical change would be something like dissolve. So I kind of want you to be taking stock of, well, what are good words to look out for? Dissolve is a really good word to look out for as a measure of a physical change. Then last but not least, physical deformation. If something is cut, dented, or stretched. For example, piece of paper, pieces of paper. Has anything changed about sorry, nothing has changed about these two things at the molecular level. There were no, like, this paper right here is largely made up of cellulose. This paper right here is largely made up of cellulose. This one piece of paper is also made up of cellulose. I didn't make any changes to that cellulose to make it anything other than cellulose when I ripped it in half. This seems like, oh, but at the macro level, at the visual level, well, you ripped it in two. I did. But the chemical compounds that make this up, and these up has not changed at all. Can I get a number in the chat if that doesn't make any sense, or a letter in the chat if, oh yeah, I got you. Okay, wonderful. So all of these are like what I consider to be really good questions to anticipate for your exam. Like, this is an example of a physical or chemical change, or select all of the answers, or select all of the answers that are examples of physical changes as opposed to chemical changes. So ripping a piece of paper is a physical change, not a chemical change. Now, chemical changes. In a chemical change, compounds are being made into other compounds. So bonds are being broken and or formed between molecules or atoms. So observations that indicate these are temperature changes, lights produced, color changes, bubbles are formed, smell or taste. On Friday, chances are you will either by design, hey, I'm going to watch fireworks, or you'll just be walking around and you'll see fireworks. You're going to see lots of chemical changes that lead to light being produced and that lead to color changes. So anytime a firework explodes, well, light is produced. A chemical has changed. Some compound has undergone a conformation, or some compound has undergone a fundamental change into what it is. And along those same lines, be safe because they also make tremendous temperature changes and that could be burns. And, also there's going to be smells with that. Okay. Does anyone have any questions about, give me a number if you are good on physical properties and chemical properties, physical changes, chemical changes, or a letter if you've got questions about those. Wonderful. Wonderful. Okay, now give me a number if you're trying to input the same number every time that I ask for a number. And give me a letter if no, I'm just slapping my keyboard. Okay. Okay. Sounds good. All right. Now we're moving on to the next section of chapter number 1, which is classification of matter. And just so you guys know, I gave you the link for the textbook. Some people like to read the textbook and have access to that, and or some people like to get access to the textbook and copy and paste it into like a reading app or something like that, that maybe they can listen to, hear the same sort of ideas from a different voice. Um, you can follow that link, but everything here is kind of originating from that. Is there significance to this is chapter 1, this is chapter 2? Not really. It's just kind of the way that the information's organized and to keep it a little bit more ordered and structured for you guys. Okay, so we have different states of matter. Now, I'd like a poll, or I got a poll question I'm going to throw up here. And let's see, launch. Yeah. Which type of property is a state? A physical or a chemical property is a state. And of course, C and D are not options. As I've said previously, there's not really attendance mandated. So I'm not, this isn't a class where it's like, oh no, I got to get my answer in the first 10 seconds. Okay, I'm going to go ahead and end the poll right there. We had 90% or 9 out of 10 folks who responded with it is a physical property, or a state is a physical property, and then one person who said no, it's a chemical property. And for those of you who answered physical, you are correct. So our physical states of matter, the 3 that we are interested in, are solids, liquids, and gases. There's also another one that is your plasma. Um, we are not so interested in that because we're focusing in on these primary ones because these are the like earthly states that we care about. Now, I like this model because it kind of shows relative kind of movements of these different things. In addition to that, it shows us or it gives us a sense of like, well, what does this look like at the molecular level? Because that is what's really pretty important. Now, I've got a simulation that I'm going to copy the link, pull up here, and then I'm going to change my share. Okay, so we got our states of matter, and it doesn't really matter what, but everything here, and this always sounds a little bit bizarre, um, but everything within here can be a solid, a liquid, or a gas. Now, water will take, water can exist as a solid. We know it as ice. Water can also exist as a gas. We know that as water vapor or steam. As a liquid, well, that's what we just commonly refer to as water. But H2O is the chemical. And what you notice, or what I want you to notice about this, is as we heat this up, as we heat up water, what slowly but surely happens. And if you look right here, you can see the temperature change. I'm going to switch it to degrees Celsius. If we increase the temperature, 97 degrees Celsius, oh, some of these water molecules are up at the top of the screen. Those are indicators of conversion to the gaseous state. Now, that's what I'm showing up there with that really wonderfully drawn circle. Um, if we cool it down, what happens? Well, if we cool this down, we can see the temperature drop. We're getting down to about 4 degrees Celsius. And our water molecules become much more organized, much more orderly. And if we continue dropping the temperature, the organization of them increases. In addition to that, what happens to their movement? Give me a response in the chat. As we cool it down, what happens to the water molecules' movement? Slows. They slow down and they just kind of get stuck. Now, does it look like I'm still cooling this system? A Y or an N in the chat. Got the cool function. Okay, I'm still cooling, but what has happened to my temperature? Got down to negative 273, and then what happened? Just sort of stopped. The reason that it stopped, and this is something that we will continue to see throughout the semester, is this is what's commonly known as absolute zero. So negative 273 degrees. Like if you ever watch a movie, has anyone actually give me a number in the chat or a letter in the chat if you have ever seen the movie or heard of the movie The Core? A number in the chat if you've heard of it, a letter in the chat if you've never heard of it. For those of you who have never heard of the movie The Core, you've learned two things today. One has to do with chemistry, and two has to do with the pop culture importance of the movie The Core. The movie The Core is about an effort to move to let's see, what is it? The Earth has stopped rotating. And they they have to get a spaceship of sorts to travel to the center of the Earth to detonate several nukes to restart the planet's rotation. Now, I bring all of this up because that's a sort of movie where they'd say, like, oh, it's so cold there. It's minus 700 degrees Celsius. Spoiler alert. Minus 700 degrees Celsius does not exist. It's a physical impossibility. The lowest temperature, not the lowest temperature recorded, the lowest temperature theorized is negative 273 degrees Celsius. This is also known as 0 Kelvin. Kelvin is the scale of temperature that scientists use and that chemists and physicists use. And that's just because that is That's looking at something like what we see here with our water molecules. This is where a molecule does not move. Not has little movements, but does not move in theory. Okay, now can I get a number in the chat if you've learned something about the movie The Core and you're interested and you're going to watch it this afternoon? A letter if I think I'll skip The Core. Maybe not just today, but every day from here on out. Okay, this is exciting. I don't know what streaming service The Core is on. Um, but I'm guessing that it's either available at the San Marcos Public Library or you can bootleg it because I think that's how I probably watched it whenever I first watched it. Actually, I think one of my a friend of mine he brought bootleg DVDs back from China and included in that was The Core. I've watched it more than 0 times, which is it's a lot. Okay, now um what I'm what I'm kind of sharing what I'm wanting to demonstrate here in addition to knowledge about the movie The Core, I also want you to see as temperature increases, our state changes, and there's a connection between movement of a molecule and the state that something's in. So we can toggle between these. Let's make something a solid. Well, water is a solid at negative 127 degrees Celsius. When you talk about an ice molecule, a solid piece of ice, are the molecules within ice moving? Yeah, very, very slowly, but they are moving. Whenever you convert it to a liquid, well, there's movement, there's more movement. And that makes sense because you can see that. You can see like water sloshing around in a cup. Now, as a gas, well, what do you notice about or when you look at this container, if we imagine this like little gray box as a chamber or as a container that we've heated up our gas in, well, the gas molecules are restricted to that, but they are going to find every nook and cranny within that. So our three different states of matter, solids, liquids, and gases, those are some of the things that make them different from one another. A solid is very structured, very rigid. Liquid, less rigid, less structured. Gas, even less rigid and less structured. Now, oh, there we go. That's what happened. Okay. Now, some characteristics about these different states of matter. Solids. A solid, whenever I think of a solid, I always just think of a brick, like a masonry brick. And I think, okay, well that brick has a defined shape. In addition to that, it occupies a set space in or a set area of space, also known as a volume. So it has a defined shape and a defined volume. Like if I were to get a brick and put it on the table in front of me and watch it go Rip Van Winkle on it, and watch it for like 60 years while I was asleep and then awaken again, what is that brick going to look like? It's probably going to look the exact same as whenever I fell asleep. Okay. So that's going to stay the same. That's defined. Now, does give me a number in the chat if you have like an object that you think of as a solid that's going to be your reference point. And give me a letter if I can't think of one. I go with a masonry brick. Okay, cool. You could also go with a PS5 or a coffee mug or a can of something. Now, a liquid. Whenever I think of a liquid, I always think of like a cup that's open because then I can see it. In addition to that, I can think about that liquid because if ever if I pick up that container and I move it around, what happens to the liquid within my cup? Well, the liquid responds. It moves. So if I picked up this coffee mug right here, which has a small amount of coffee in it, and I tilt it to the side, and then I bring it back to center. And I sound kind of like I'm doing my best to sound like a yoga instructor there. Now to the left, and then bring it back to heart center. Then we'll go to the right, bring back to heart center, and now to child's pose. When this coffee is in child's pose, just this base starting point, or when it's to the left, can you give me a number if you can visualize that liquid in that cup kind of sloshing around? Give me a number if you can visualize it, or a letter if no, I can't imagine that. Okay. Okay. So we're at heart center here. We're at the starting point. Then I move it to the left. Does the liquid have the exact same shape when it's like this as when it's like this? Give me a Y if yes, it has the same shape, or an N if no, it does not have the same shape. I was going for it's not going to have the same shape because of the fact that, like, if you think about the surface of it, the surface will tilt to the side and that surface will sort of spread out. If it's upright like this, it's a perfect cylinder. But then if I put it at an angle, well, it's no longer a cylinder with a flat top and a flat bottom. Instead, it's going to have like, well, it's going to look a little bit different. Now, what is not going to change there is the amount of space in 3 dimensions that the liquid occupies. So the volume will not change. So liquid has an indefinite shape, but a definite volume. Indefinite shape, these two coffee mugs are slightly different. So if I start out with coffee in this coffee mug and then I pour it into this coffee mug, the volume is going to be the exact same, whether the coffee's in here or whether it's in here. But the shape, yeah, they're both cylinders, but are they going to have the exact same dimensions? No, they are not. Because this mug is a little bit wider than this mug. So the shape is going to differ a little bit. Now, a gas. A gas is not going to have a defined volume. It's also not going to have a defined shape. And I always like to reference this because it illustrates this point very well. Um, Whenever I was in 6th grade, I remember there was a girl who she brought a stink bomb to school. Can you give me a number in the chat if you're familiar with what a stink bomb is? If you are waiting for me to say, can you give me a letter? Then congratulations, you don't know what a stink bomb is. But I think it's pretty self-explanatory. It's something that stinks. Now, this girl brought a stink bomb to school, and they were little glass vials, and she went into the bathroom and she smashed it in two. And what happened then was the gas that was contained in that stink bomb was released. And what that gas did was it filled the bathroom. And our school, thankfully, I don't know why it wouldn't, but thankfully it had central air. And so it had duct work. So it had an AC vent system. And so that gas filled the bathroom. Could anyone add to the chat? And this is a lengthy response, but what is it going to do after the gas fills the bathroom? You can go to the air ducts. And ultimately, Julia, you're absolutely right. It's going to fill the entire school. And it got to some areas very quickly. Oh, good use of the word diffuse, Julia. Good job. It ultimately made its way throughout the entire school. And, some areas were a stronger odor than others. Um, but it stank. And it was awesome because then we got to go outside And then they just gave us an early release because it was just a matter of time. They had to open the doors to all the rooms and to all the exterior of the building to get the air to circulate through, to basically get that odor to spread out everywhere. Now, my point there is that gas had no defined shape. It first had a defined shape of being in the container. But then, whenever you gave it a larger shape, the bathroom, it filled that. Then, whenever it saw that it could go into the duct system, it filled the duct system. So it was not defined, it was not restricted by that. Then, if you think about the volume of that little glass container was super small. The volume of that container, well, whenever the new container was the bathroom, the volume of the bathroom is much larger than that little glass vial. So gases have no defined shape. They have no defined volume. They have kind of a limited, I guess you could say, of a defined volume, but that definition is only the definition of the container that they're found in. So there we go there. Now, whenever we talk about our three states of matter, we've got solids, liquids, and gases. Whenever we kind of talk about classifying matter, we then want to go on to say, okay, well, what is that matter? Is that matter a substance, a pure substance, or is it a mixture? So a pure substance would be something like, and actually, I think if we go like pop superstar Drake and start at the bottom right here, if somebody said, "Hey, cool, I got a gold coin for you," well, it's 50% gold and it's 40% brass and 10% lead, but that's gold. Um, what percentage of that are you super pumped about? Or are you thinking like, oh yeah, that's high value? Are you give me your number in the chat? Are you pumped about all 100% of it? Maybe you're super optimist. Or are you pumped about the 50% that's pure gold, the 10% that's lead, or the 40% that's brass? I think exactly. I think most everyone's going to be like, huh, that's neat. You got a coin. Well, yes, that's very appropriate to be concerned about the lead. Keep it out of the ground, water supplies, children's mouths, adults' mouths, though my understanding is that lead has less of an impact on adults because it's like a developing brain issue. But nevertheless, that's not like oh yeah, go chew on some lead. It's really tasty and fun. Um, yeah, you're interested in the pure gold. If somebody came up to you and they're like, "Hey, I got two coins. One is pure gold, 100% pure gold, and then one is a mixture." Chances are you're going to be like, "You know what? I want that one that's the pure gold because I could take that to a jeweler and I could sell it to them. I could take it to eBay and sell it there." In addition to that, gold has tons and tons of industrial applications. Gold is great at conducting electricity. Uh, it's also pretty, but you're interested in that pure substance. So, gold, for example, a gold ring, if it's got lots of value, it is what is known as a pure substance. And gold is on the periodic table as a U, as a pure substance. So if you go to a jeweler and you get something that is pure gold, that thing has nothing but a U. It looks at the molecular level like this right here. And I hope that my scribbling makes that clear that, oh yeah, I know what he's talking about because he scribbled I don't know what on it. Now, if by comparison, um, so there's like a quantifiable value to gold. Um, there are things that are composed of two or more elements. Can anyone give me a substance that is composed of two or more elements that maybe comes from a faucet and Um, Aquafina makes it, not the comedian, but instead the I think Coke product. Give you a hint. H2. Yeah, water. Perfect. H2O. That's composed of two or more elements. And that is what is known as a compound. So you can have a pure compound. You can also have a pure elemental substance. So water is a substance that can be a pure compound. Gold is a pure substance that is made up of a single element. Now, other things, other classifications or other big classes of matter are mixtures. Now, this gets a little bit hairy and a little bit confusing, but when we talk about a mixture, we define them as heterogeneous versus homogeneous. I actually used this term yesterday when I was talking about drinking a whey protein shake. Whenever you shake it up a whole lot and it goes into solution perfectly, that protein is super soluble and you're ready to drink it. That is what is known as a homogeneous solution or homogeneous mixture. That's the one where you're like, this is great. I love this. Um, from my experience, there seems to be like a price point, really low cost whey proteins. What do? They don't go into solution very well because they're not very soluble. And so chances are you're going to get a heterogeneous mixture from that. And what that means is that you'll add the whey protein, maybe even throw it in a blender or get one of those frother things to mix it up really well. And then you'll take the frother out and you'll be like, oh man, it's kind of gross looking because I see chunks. I see chunks of protein floating around in there. Oh man, I don't like that very much. That would be a heterogeneous mixture where you could pick out the chunks of protein and you could separate that from the clear solution. So you have heterogeneous and homogeneous mixtures. Now, of these mixtures, they are composed of two or more substances. I think I just came up with an idea to kind of illustrate this. Um, has anyone ever heard of? I think the I think the name is Goldschlager. Give me a number if you've ever heard of that, or a letter if you have no clue what I'm talking about. Dang, I think that's the name. Well, at any rate, um, it is a it's a liquor. I think gold. I'd have to look up the name. It's a liquor that has small gold flakes in the bottom of it. And I think the idea is like, look at how wealthy I am. I will not only like I can just throw money away. I am going to drink a drink with gold flakes in it. Be impressed. Now, those gold flakes, they float around at the bottom of that bottle. Now, my question for you guys, and maybe I could just change the example. If I got a piece of paper and shredded up into a bunch of small pieces, and then I gave you a cup of water, and I threw the paper into that cup of water, and I said, "Aha, there you go." Is that a mixture? Yes or no? A mixture of pieces of paper and water. Y or N? Yeah, it's totally a mixture. Now, follow-up question. Because we want to be able to classify something as a heterogeneous or a homogeneous mixture. A homogeneous mixture is where you look at it and it looks the exact same through the entirety of it. A heterogeneous mixture is where you kind of look at it and you're like, oh, well, there's a chunk of something, and there's a chunk of something, and then there's an area where there's not a chunk of something. This paper water, where again, the pieces of paper are about this big, and I just drop them into the water. Is that a heterogeneous or a homogeneous mixture? Give me a M for homogeneous or a G for heterogeneous or a T for heterogeneous. Sorry for changing that on you. That would be a heterogeneous mixture because these pieces of paper, what does paper do whenever you throw it in water? It doesn't dissolve. It doesn't disappear rapidly. Instead, it's going to be floating around in that solution. So that would be an example of a heterogeneous mixture. Okay, we want to be able to classify everything as, is it a pure substance or is it a mixture? And then of those pure substances, is it a pure substance of an element or is it a compound? If you have two or more elements, it's a compound. If you have a single element, that's a pure substance that is, well, an element. A mixture is two or more substances. So I think a good example is to come up with something like, you know, gold flakes in water. Okay, well, gold flakes, that's your element, pure substance. And then water is a compound that is also a pure substance. You mix those two things up, and you've got a heterogeneous mixture. There are some things that are going to go into solution perfectly well. For example, salt water. Let's think about that. Salt water. Well, H2O, that's a compound. NaCl, that is a substance, that is a compound. Okay, so we meet with the Cl is a compound. Does everyone agree with, give me a number if you agree with what I've just typed and you understand what I just typed, or a letter if you don't follow. Okay, wonderful. Now, if we make this salt water, and just imagine that you're making this at home or something like that, as opposed to like going to the Gulf and getting water. Um, Salt water, where you just get a glass of water and you add a bunch of salt to it, is that going to be a heterogeneous or a homogeneous mixture? Give me an M if you think it's a homogeneous mixture, or a T if it's a heterogeneous mixture. And whenever I say salt, I mean just get your salt shaker and that's it. Not like adding a pound of salt to a glass of water. Ah, you guys are asking really great questions. Before or after it dissolves? I'm gonna go with before it, or sorry, after it dissolves, because we're just gonna add a little bit. And yeah, we'll stir it up just to kind of give the illusion or ask the question, does this dissolve or not? You guys both asked fantastic questions there because another kind of follow-up I'm sure that you have is, well, what about the amount? If you add like one pinch of salt, yeah, that's going in solution just fine. And that would make a homogeneous mixture. Whereas if you got a handful of salt and poured it into a glass of water, well, that's not all going to go into solution. And that would make a heterogeneous mixture. So I guess my point was salt water, chances are it's going to make a homogeneous mixture. And so I'm happy that we're kind of getting into this sort of question because there's subtlety to these questions. It's not just, oh, well, it's this or it's this, the end of the day, or that's it. Instead, we got to ask some of these questions of the situation. And so to the point, it says, perfect. I like it. I like it a lot. That's great. Wonderful. And you're right. Then it kind of crosses over and then it's a heterogeneous mixture. Now, for other classes, and this is like third or fourth level chemistry, you get into a solution being saturated. But we don't really get into that in this class. But that is something that people do. They make what's known as a saturated solution. So great observations, everyone. Okay. Now, an element, well, elements are composed of one type of atom. This always throws people for a little bit of a loop because oxygen, O2. When you talk about oxygen, it exists as two atoms, but that's one type. They're identical atoms, but there's only one type of them. A compound is composed of two or more elements. H2O, water. Well, hydrogen and oxygen. Those are different. Hydrogen and oxygen are different, which is why this is a compound. Table salt. Those are different, which is why it's a compound. Now, we've got atoms. These are the smallest characteristic parts of an element, and a molecule composed of two or more atoms. So anytime I talk about a molecule, the definition is two or more atoms. Now, an important point looking at this is water, H2O. Those are three total atoms. Two of them are different. Carbon dioxide, three total atoms. Two of them are different. O2, two total atoms. They are the same, but all three of these are molecules. Au, by comparison, well, that is a single atom of gold. Okay, we are going to go on now to our next slide deck and kind of go through this a little bit. Let's see. Okay, we got about we got about 9 or 10 slides on this slide deck that we'll go through. Okay. Full screen on this. Now I'm moving on to the measuring matter, or the day 2 slide deck. And just so you guys are all on the same page as me, today, Tuesday the 1st, what I had scheduled for today was the day 1 slide deck. So we're making a little bit of forward progress. So we're talking about measuring matter. Now, the units of measurement that we need to be concerned with, we need to be concerned with quantities and the units that are used for them. So these are what are known as the SI units, or International System Units. These are units that are in any science around the world. These are the units that people are going to use. When they talk about the length of something, they're talking about a meter. Mass, grams, volume is liters or cubic meters. Time is going to be measured in seconds. Temperature. I mentioned Kelvin earlier whenever we were looking at states of matter and how they change based on temperature. But we will see kind of both of these. And being able to convert between Celsius and Kelvin is an important tool. And we will talk about that later today. And then last but not least is the amount of a substance, and that is moles. Can you give me a number in the chat if you're familiar with what a mole is in science, and a letter if you've never heard of that before? Okay, great. So just to give you a little bit of like a planning ahead and thinking ahead, a mole of something is really just it's a definition, to put it simply. For example, if I tell you that I have a dozen coffee cups, how many coffee cups do I have? Add it to the chat. Well, a dozen, that word dozen, that's a definition. A mole is the same thing. And so that's a tough thing, because when we talk about a mole of something, we are talking about a very, very large quantity. And that quantity is 6.02 times 10 to the 23rd. So a very large number. Anytime you see this times 10 to the 23rd, that has to do with what's known as scientific notation, which we're going to get into in just a moment. But I want you guys to be familiar with what a mole is as the very large number and as a definition. Now, here it is again. A mole, I'm going to go ahead and say equals 6.02 times 10 to the 23rd. 1 mole is equal to 602,000,000,000,000,000,000,000,000,000,000,000,000,000,000 particles. That is the same as 6.02 times 10 to the 23rd. Okay, now these two numbers that I'm going to put a big box around are the same because we use something known as scientific notation. We have a number and then times 10 to the n. And that times 10 to the n is the number of times that you move a decimal. Now, to visualize that, okay, can you give me a number in the chat if you are familiar with this scientific notation or a letter? If no, I've never seen that before. Not necessarily like, oh yeah, I've got this down, but just, yeah, I've seen it before. Okay, good. So it seems like most folks have seen it. Now, there are some rules with this, and it does get a little bit tricky and a little bit hairy, but we're going to go through. Being able to convert from a number in what's known as long form notation, which is what you see here, to scientific notation is really important for this class. So if we were to take the number 8675309, which is a song by Tommy Tutone, that song is 8675309 Jenny. It was popular in the 1980s. If we were to write that number in scientific notation, we'd write it like this. So if we're taking something from the long form to scientific notation, in the long form, we've got a decimal place that's kind of implied to be right there. We are going to move it so that we have one number followed by a decimal, followed by the remainder of the numbers. We're going to move it 1, 2, 3, 4, 5, 6. So we would write that as 8.675309 times 10 to the 6th. So then if we were to look at, not do this as a poll, but look at these numbers as a comparison. Ah, rats, why did that do that? These numbers right here. Which one of these is the largest? We've got 2.4 times 10 to the third, 240, 24,000, and 2.4 times 10 to the minus third. Okay, so what I want to do rather than do this as a poll is work through each one of these and kind of convert them from what they are to what they could be. So this number right here, A, that is written in its scientific notation. So we are going from scientific to long form. That's what our first one is saying. And what that is going to be is 2400. So we're going to move that decimal, or we're going to move this number 3 places. 1, 2, and 3. So 0, 0. Can I get in the chat a response if, okay, yeah, I got that. That makes sense. When I'm going from a number if I follow that, and a letter if no, that doesn't make sense. Okay, great. Now we're going from long form to or scientific notation. Here are decimal places right here. When we go to scientific notation, we have to have one digit followed by a decimal, followed by the rest of the number. So 1, 2. So this is 2.40. Am I done? Give me a number if I'm done, a letter if no, I'm not done. And I should, sorry, whenever I say done, I mean, I should submit this and I will be right. And one way to think about that is 240 the same as 2.40? No, those are different numbers. So what I'm going to do is add on to this and say 2.4 times 10 to the, now give me the, in the chat, give me the digit that I should write. Two, perfect. Wonderful. So 2.4 times 10 to the second. This next one, answer option C, is long form to scientific. Whenever I do that, I've got a decimal right out here. 1, 2, 3, 4. 2.4 times 10 to the fourth. Okay, so then our last one is we're moving a negative decimal. We're going from scientific to long form. Times 10 to the negative third. Well, in this case, moving my decimal, 1, 2, 3. So this is 0.0024. Now, how did I know to move my decimal to the left? Well, because I have a negative decimal or a negative exponent. One way that I always think about it is positive exponent means, well, number larger than 1. Negative exponent means number smaller than 1. So if ever you're confronted and you see an answer option like answer D and you're like, oh crap, I can't remember, what do I do? Do I move the decimal left or right? Well, if you fall back on this idea that the negative exponent means the number is smaller than 1, then you're going to arrive at 0.0024 as opposed to 240. Or, yeah, 240, I think. Okay. We'll go on from there. Writing the number in scientific notation, 0.000123. With scientific notation, what we always need to have is we need to have two numbers, or sorry, we need to have one number followed by a decimal place, and then the rest of our number. We did not include all of these zeros when we wrote it in scientific notation. And lots of times when we write a number in scientific notation, we drop some numbers. But the numbers that we drop are always zeros. We never drop a non-zero digit. Okay, so just as a, yeah, so we're going to do about 10 slides on this slide deck, and we're at, yeah, we got a couple more. We've got prefixes. If anyone's ever watched the show Breaking Bad or any other show that has to deal with drugs, well, then you're probably familiar with kilos. That is times 10 to the third. That's 1,000. A milli or a nano. Milli is times 10 to the minus third. Nano is times 10 to the ninth. Which measurement is the smallest? Well, we've got 2.4 grams. That's your base unit. 2.4 milligrams. 2.4 nanograms. Okay, well, really, these are, we could order these from smallest to largest. Largest is kilograms. Smallest, second largest, and third largest. I think that it's helpful anytime you can come up with something that's like relatable. Um, for example, if take an ibuprofen or Tylenol or if there's any sort of antibiotic or medicine that you take on a regular basis, look at that bottle. Chances are that bottle might be like, oh, take 10 milligrams of this. Okay, well, that 10 milligrams is in that capsule, and chances are that 10 milligrams is the drug that's in there, plus a bunch of other stuff. Not a bunch of other stuff, one other thing that's a filler, basically like salt. Um, but I think it's relatable to think about things like that because then you can kind of compare, oh, a kilogram is this, a milligram is this. Okay, so then smaller than a milligram would be a nanogram times 10 to the negative ninth. 25 nanograms. Let's see, let's take that and write that in scientific notation. So that would be the same as 25 times 10 to the negative ninth. Now I want you guys to go ahead and do this on your own. I'm going to do it as well. 25 nanograms, and I'm converting this to grams. That's what I'm doing whenever I say times 10 to the negative ninth. I'm moving this decimal place. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0. And I make these little cloud shapes so that I know where to put my zeros. Do you think, oh man, that's stupid? You should be better at this than that. Okay, well, I I don't want to be a grouch about it. That's how I do it. And if you want to be a grouch about it, that's not my problem. So 0 point, and let me write it out with a 0.000000025 grams is equal to 25 nanograms. And 25 nanograms is equal to 25 times 10 to the negative 9. Okay. So with these metric prefixes, we have this entire range here. For your exam, what I will ask you about is I will ask you about this range right here. I will not ask you anything beyond that. I think I've got one question on the practice exam that compares quantities outside of this, but on your actual exam, you're not going to have anything outside of this. And if I accidentally put something outside of this range, well, that's a bank error in you guys' favor, and I will give you credit for that. Now, what I want you to be able to do and how this is useful is to make conversions. Say, or an example question would be 12.5 megagrams is equal to how many? Well, let's go with kilograms. Okay. So if you were asked that sort of question, then what you could do is say, okay, well, let's compare this. 1 kilo and mega. Okay. These numbers right here, those are referencing or comparing to one base unit, so a gram. So 1 megagram is 1,000 grams. Or sorry, 1 megagram is 1 million grams. 1 kilogram is 1,000 grams. So 1,000 grams equals 1 kg. So then if we were comparing these two things, what we could say is, well, if you have 1,000 kilograms, that's equal to 1 g. Can I get a number in the chat if you follow these sorts of conversions and the need to be able to do these sorts of conversions? And a number in the chat if you do, and then a letter if you chat if you're like, I'm confused about this. Okay. So when you're doing these sorts of conversions, you always have to reference like your base point. Um, and it does take a little bit of like processing of information. And sometimes it's helpful to think about a quantity that you're familiar with. So if you were to say something like, I have one, answer this in the chat. If I tell you that I have $1 mega, how many dollars do I have? If I tell you that I have $1 mega, that means I have $1 million. If I tell you that I have $1 tera, I've got arguably that would be $1 trillion. Exactly. Because one other thing that you could do with these numbers is you could say, okay, this is 1,000, this is 1 million, this is 1 billion, and this is a Bezos. Or, sorry, a trillion. I didn't get invited to Jeff Bezos's wedding, but that's because I'm not a wealthy person. Um, and I would not have gone because I don't like flying. So that I think is a good way to think about these things. So going back to this conversion from mega dollars to kilos, if I say we'll convert from a kilo to mega, you have one you have $1 mega, and you've decided to make stacks of $1,000. How many stacks do you have? All of these stacks have $1,000 each, so you have 1,000 of them. Now, if I were to change this to change it from mega dollars to giga dollars, then it wouldn't be a question of, well, sorry, from giga to kilo. If you have a giga dollar, how many $1,000 stacks could you make? You could make 1 million of them, which is kind of insane to think about somebody being a billionaire having 1 million stacks of $1,000. So be able to convert between these numbers. Try to come up with something that is tangible that you can relate it to. And think about this base point in the middle right here. That would be your base unit, like $1 or 1 gram. I think that it's helpful to play around with these prefixes using like a dollar or something like that, just until you get a little bit more comfortable with it. Now, some of these have repeating units, but there are some slight differences. Lowercase g means gram. Uppercase G is giga. Lowercase k is kilo. Uppercase K is Kelvin for temperature. M could be either a meter or a milli, either a prefix or a base unit, and then capital M is mega. So make sure that whenever you're looking at these things that you can kind of understand what you're being asked about. Now, this right here is the digital balance. And you can see on that digital balance, you've got an apple. And that apple weighs 172.3 grams. Or you could say that it is, in scientific notation, 1.723 times 10 to the second grams. In kilograms, you'd say 0.1723 kilograms. If you have a digital balance, I think that might be helpful to like throw something on there and just play around with those things. Now, measuring volume, we measure in milliliters, and we ask the question, what is the volume of this? Here we've got 45.0 milliliters. In liters, that would be 0.0450 liters. Both of these instruments, this digital balance and this graduated cylinder, digital balance and graduated cylinder, those give you the precise measurement. If I told you that this apple had a mass of 172.30, am I right or wrong? Add to the chat R for right or W for wrong. Okay, so if I said that it was 172.30 grams, that would be basically the same as me saying, well, it's actually 172.32 or 173.33 or 173.31. Those three values, the 173.31, 2, and 3, those are just as correct as 0.30 because this instrument right here, and anytime you use a digital balance, it's being honest with you. It's telling you this is its limitation. It can't measure to the hundredths position. So it's not going to give you a value in the hundredths position. It's telling you the best I can come up with is this apple has a mass of 172.3. If it was more precise, if it knew better, it would tell you. Now, with that in mind, there we go. This graduated cylinder here. Well, you'd look at this number right here and you'd say, okay, well, there's a 40 and then there's a 50 and my solution's basically the exact same. There's something called a meniscus. And when you look at this instrument, it tells you, or when you look at measuring something on a graduated cylinder, it can tell you like, okay, this is 2.0. So this is 45.0 milliliters. It's not any better. It's not any worse than that. It's 45.0. Now, measuring the length of something, you do the same sort of thing. So here we've got a pencil that is starting at 12 for some reason, going over here to 5. Okay, actually, here's 6. So 15 centimeters, 16 centimeters, 17, and there's our point right there. It looks like it's about 17.2 or 17.35 centimeters if you got really precise about that. And you can convert that into inches, which would be 6.831 inches for the length of this pencil. So all of these markings on a ruler or a graduated cylinder, they are precise. That is a specific measurement. If you go above that or below that, you can make an approximation, but you lose some amount of precision there. And measuring time, when we talk about seconds, this right here, how many seconds are in 6.5 minutes? 390 seconds. This digital clock measures all the way to a single second. And so we can get to, well, 391 seconds. And then this is actually, I got a little bit ahead of where I wanted to, or where I anticipated, but I feel like this is a good point. Nope, 2 more slides. Measuring temperature. Anytime you're given a temperature in degrees Celsius, to convert it to Kelvin, and this is one thing I want you guys to be able to do, convert from degrees Celsius to Kelvin or degrees Celsius to Kelvin. So if something is 32.7 degrees Celsius, you add 273 to it, and you end up with 305.7 Kelvin. If by comparison, the temperature is, let's say that you're told that it's 412 Kelvin outside. What is that in degrees Celsius? Well, that would be 412 minus 273, which would be 139, I think. Yeah, 139 degrees Celsius. Which would be like 260 degrees Fahrenheit. I want you to be able to convert from Kelvin to degrees Celsius and degrees Celsius to Kelvin. I'm not going to ask you here. So be able to do that. Um, then we'll look at digital or all of our balances or all of our temperatures. Here's our temperature scales. These are the two that we will be focusing on in this class, Celsius and Kelvin. 373 Kelvin is the same as 100 degrees Celsius, which is 0 degrees Celsius is 273 Kelvin. Negative 273 and 0, that's that absolute 0 point that we talked about previously. I'm going to ask you about doing these conversions. There might be a small number. So be ready with those. When it comes to conversions between Fahrenheit and Kelvin and degrees Celsius, I want you to know major points. These right here and these right here. Average body temperature, room temperature, freezing point, and boiling point. I want you to know 212, 98.2, 68, and 32. Those are Fahrenheit temperatures. I want you to be able to convert or know, kind of memorize those, how they relate to degrees Celsius and Kelvin. Okay, so that leaves us to density. And that's actually where I'm going to stop today. So if you have some questions, you're welcome to hang around. Other than that, though, I hope you have a wonderful afternoon. Thank you guys for coming to class. We will pick up here tomorrow talking about density and measuring density and converting, using density as an important value. But if anyone's got any questions, you're welcome to hang around. Other than that, I hope you have a great day, and I will see you guys tomorrow. I'm going to stop my recording right